Welcome to our video summary of an exciting advancement in the field of precision medicine. Today, we are exploring the insights from the article titled Empowering Individual Trait Prediction Using Interactions for Precision Medicine from Gola and Koenig 2021. Before we start, we must know what is precision medicine. Precision medicine is also known as personalized medicine. Is a medical approach that tailors treatment and healthcare strategies to the individual characteristics of each patient. For example, individual risk prediction for complex diseases like coronary artery disease. However, a key aspect of precision medicine is developing prediction models that maximize their predictive accuracy. So, if we look at the standard approaches such as generalized linear models, it may be ideal, and machine learning is tempting to make predictions. However, most of these algorithms focus mostly on main or marginal effects of a single features in a dataset. In simpler words, we need algorithms that can detect interacting features, and we already have that, which is multifactor dimensionality reduction, or MDR. So, in this article, the research developers further develop the model-based MDR, or MBMDR, a robust enhancement of the original MDR algorithm to enable interaction-empowered individual prediction. So, how have they done it? Basically, a simulation study was conducted to compare their proposed algorithm, the MBMDRC, with two leading prediction algorithms, the random forest and the elastic net. They evaluated the performance of the three algorithms across 8 different scenarios, each with varying underlying effect structures. Here are the 8 consecutive scenarios of genotypes of single nucleotide polymorphisms and their interactions. In Scenario 1, which involved one single SNP, and Scenario 2, which involved 5 SNP, where only main effects were simulated, all algorithms demonstrated identical performance levels. Then we can see that when the sample size increases, the median performance of all algorithms improves, and the variability in performance decreases. Comparing Scenario 1 and 2, it shows that the performance is dependent on the number of SNP combinations. This is expected, as the total heritability increases with the number of SNPs. In Scenario 3, which involves one pair of 2 interacting SNPs, MBMDRC models demonstrate the highest median predictive performance across all sample sizes. In Scenario 7, that includes both main and interaction effects, MBMDRC models dominate over the other 2 algorithms when sample sizes exceed 200. In the last scenario, Scenario 8, still MBMDRC models achieve at least a similar performance as the other 2. Also, the median performance for sample size 2000 is slightly better than the other 2. So, how did they validate the simulation study? Basically, they compared the performance of the 3 algorithms on a dataset by the North American Rheumatoid Arthritis Consortium, NARAC. It turns out that when applying the 3 algorithms to the rheumatoid arthritis dataset, it shows no significant differences in their median performance. Now, what exactly are the main findings of this study? We can see that their new algorithm can use information hidden in interactions and outperforms the other 2 state-of-the-art algorithms, the random forest and elastic net, by comprehensive simulation study and by application to real data. However, when tested on the actual rheumatoid arthritis dataset, their new algorithm's performance was not significantly different from that of the competitors. One limitation of their new method is that its runtime increases exponentially with the number of features in a dataset. This makes applying their new method to genome-wide datasets challenging and highlights the need for further improvements. In conclusion, they concluded that incorporating interactions between features can improve prediction performance and should be taken into account in future efforts to advance precision medicine.